Duncan, we very much look forward to listening. It's all yours.
Okay, thank you, Maria.
So just one more logistic question. Do you prefer people to interrupt to make it more interactive, or to wait with questions?
Interactive is perfectly okay.
Okay, we'll send an email to everybody. Okay.
Yeah. I may not be able to monitor or I won't be able to monitor the chat or people raising hands. So
no, we will let
just
you
chime
know.
in.
Dan and I will coordinate.
Okay, that sounds great. Okay.
Thank you.
Okay, can everybody see my screen?
Yes.
Okay, great. So thanks, Dan and Maria, for the opportunity to speak. As Maria said, the topic of today's talk will be exploring future power system stability. And I'll set that up with first a definition of how I view what it means for systems to have low inertia. So if we think about the over 100-year history of electric power systems, they've been dominated by what we call rotating machines. And so our sinusoidal voltage waveforms are produced by very large spinning masses, big magnets spinning around to produce a voltage, and then that delivers current to loads. So these generators are typically what we call synchronous machines, and the rotors then very rigidly connect to an existing system frequency. So with that large spinning mass at 3,600 RPM at 60 Hertz, what that means is that with that rigid connection between the grid's voltage waveform and the synchronous machine's voltage waveform, the inertia of the device is available to the grid to smooth out some types of disturbances. So people often talk about how when there's a disturbance on the system, there's a conversion of the inertia of the rotating machine actually into a current to source the kinds of disturbances that might arise. As we move to electric power systems that are dominated by power electronic converters, meaning inverters, so think about photovoltaic systems or battery systems or wind turbines, then this inertia on the system, that natural reservoir of inertia tends to decrease. And so that has raised a lot of questions about whether it might be harder to tightly control grid frequency. And this is something that researchers have been thinking about for at least 10 years now. But one of the things that I want to talk about today is whether that's all. Is it just frequency that we need to be concerned about? And is it possible that other types of undesirable dynamics might occur if we have a system with less inertia, which also comes with it more complex converters that have additional control loops inside of them? So let me talk a little bit more about these ways that people think about stability and this decade plus history of people thinking about frequency as being a measure to be concerned about. So this is a paper taken, or a figure taken from a paper a study led by Joe Edo and John Undrell now actually 11 years ago, where they were asking questions about the Western interconnection and what would happen to system frequency in situations where you had high penetrations of wind generation. And they looked at things like rate of change of frequency, the nadir in frequency, and steady state frequency. And a number of projects have gone on to think about these types of issues emerging and ensuring that, for example, the rate of change of frequency is not too high, and the nadir is not too low, in order to ensure that the dynamics of the system are desirable. But there's also some interesting recent work where people have started thinking about higher order dynamics, both in terms of small signal stability and transient stability in other state variables other than system frequency. So for example, voltage. So this is a figure that I'll talk about a little bit more later from a paper by Yashen Lin and Brian Johnson and Sairaj Dople, looking at the potential emergence of unstable voltage dynamics in low inertia power systems. So before I dive into that, I just want to give a very brief overview of inverter control. And this is something that may have been covered in earlier seminars this fall. But just to make sure we're all on the same page, something that I think it's becoming increasingly common for people that talk about these issues in their talks to say, Well, there's still a lot of kind of controversy over what it means to be grid following versus grid forming, and the jury is out on exactly how we're going to define these things. But I'll do my best here, and then if we want to have discussion about it, we can. So if we think about a conventional power electronic converter, so the large majority of converter interface generation on the grid today follows this paradigm of what we call grid following. So the idea is that these devices will have set points for real and reactive power, and then sense grid frequency with a phase locked loop and track it exactly. So the basic idea is that that converter is listening to what's happening on the grid, and just say whatever the voltage is, both magnitude and frequency on the grid, I'm going to go ahead and track that, and then deliver my real and reactive power set points subject to those voltage waveform conditions. So a grid forming inverter is slightly different, where it may have real and reactive power set points, but also is seeking to deliver some voltage magnitude and frequency. And then where the secret sauce is and the way that these things work is they'll adjust their voltage magnitudes and frequencies in response to measured deviations from their P and Q set points. So droop control would be one example, where when P and Q exceed their set points, then you'll reduce your voltage magnitudes and frequency in proportion to that excess. So this is a topic of quite a lot of interest. DOE just recently announced it'll fund a $25 million research consortium on grid forming inverters, and this is something that I'm participating in and have been running a seminar series this semester on. So let me just talk a little bit more then about the upshot of thinking about the way that these devices, grid following versus grid forming, work. So a grid following converter will instantaneously control its real and reactive power, will not generally source fault current, so control against having to deliver a fault current in response to what might be happening on the system. But of course can't operate standalone. It needs to listen to that system voltage waveform. And for obvious reasons then can't achieve 100% penetration, whereas a grid forming converter can. So we can have a network of grid forming converters that can work together to power share and achieve 100% penetration by instantaneously balancing loads without a centralized coordination, and that's done by something like a droop control mechanism. So just maybe then to kind of distill everything as much as possible, I see the upshot here as being that grid following converters are often easy just to think of as a negative load, and they're things that are more comfortable to system operators. But what I'll show you is that the control loops that exist within grid following converters to regulate current and voltage themselves can generate system level issues in the right conditions. Whereas grid forming converters, that's our current solution to power sharing in the absence of synchronous machines. From a systems perspective, these are pretty exciting devices because we're basically talking about removing that workhorse of electric power systems, the synchronous machine, and trying to replace or even improve upon the way that those devices have kept our frequencies and voltages stable over the years with something that's completely configurable, a power electronic converter. Okay, so let me give you a little bit more of my thoughts on why this is really interesting from a systems perspective. So dynamics in power systems vary over many, many orders of magnitude. So we can break up those dynamics into wave phenomena like lightning propagation or switching surges, electromagnetic phenomena such as what we typically thought about are stator transients or subsynchronous resonance, where the stator is the electromagnetic part of the fixed, not moving electromagnetic part of a synchronous machine. Then we can also think about even slower dynamics, electromechanical phenomena. So think about the actual conversion of inertia by slowing down the machine to power, or valve dynamics and things like that. Sorry, just let me focus there. And then we can think also then about thermodynamic phenomena, which are the valve dynamics of the inputting of fuel into the prime mover of a synchronous machine. So this varies over many, many orders of magnitude. And the thing that I didn't talk about yet on this figure is where we place inverter-based controls in this map. So historically, all of the control loops have sit on much slower timescale dynamics. So for the synchronous machines, those sit over here in the hundreds of millisecond to in second timescale and beyond on their timescales. Whereas when we think about inverter-based controls, their fastest inner control loops on voltage and current will be happening depending on the switching frequency of the converter itself in the tens of milliseconds range. And then the actual PWM control of the converter is even faster. So if it's, let's say you're switching at 1 megahertz or 100 kilohertz, then you're typically going to be an order of magnitude slower on your PWM control on the converter. So what's fascinating, I think, from a systems perspective here is that we're now embedding control loops into a system where at timescales in the system where historically these were passive phenomena, that is lightning propagation, switching surge, state or transient. But now we're putting active control into the system on those timescales. So the question becomes, well, what could that generate undesirable dynamics that we haven't thought about before? So these questions have actually been posed by, I think, an excellent high-profile study sponsored by DOE, a research roadmap on grid forming converters, where they ask questions like, if we have heterogeneous systems containing grid following and grid forming inverters and synchronous machines, what can we do to guarantee that those devices will operate in a way that guarantees frequency regulation and stability in other state variables than frequency? They also pose questions like, are there interactions between machine excitation systems and inverters with either grid forming or grid following controls? And then they just make this statement, which I think is, I strongly agree with, which is that assumptions that underlie the current generation design and control approaches need to be re-examined, modified, or even redefined. And this in large part stems from these new timescales of control emerging. And I think a lot of open questions that I won't be able to fully address today about what system physics we need to actually be contemplating when we think about large-scale systems and their dynamics. Okay, so now I'll get to the meat of the talk and the questions that I want to address. So I've got 3 things that I'll talk about. The first is addressing this question: are low inertia large-scale grids small signal stable? And the answer that I'll show you is that it's not always the case that those types of systems will be small signal stable. And I'll do this in a way where I attempt to look at factors that appear to drive destabilization. And a preview of this result is that you'll see that there are interactions between the control loops on the synchronous machines and the power electronic converters that seem to matter in important ways. The second question, this is just going to be a very brief dive into a paper where we've been trying to understand what can be done to influence stability in low inertia grids. So in a way, responding to what we're finding in this first question, that there are small signal instabilities that arise. This paper is a beginning of an attempt to address some of those emerging unstable dynamics. But I'll actually frame it in a way where we're thinking about, because of the way that the project was actually funded, we're thinking about this in a way where you actually have an adversary that's seeking to destabilize a system. But I'll offer some preliminary ideas on how we could just reverse that to make it a control loop that actually attempts to stabilize the system. And then the third question, and this is an area of, that I'm really excited about, where we're pushing a number of balls forward to try to address what we think is the future of computation and power systems analysis. So I'll try to make a case to you that complexity matters. I've already started making this case that complexity matters much more in low inertia systems than in a traditional synchronous machine dominated one. And I'll describe very briefly a new tool that we've developed called Power Simulations Dynamics, or PSID. And I'll talk about some ways that we're using what I'll call a sandbox. This PSID, I think, is a very interesting research sandbox. And I'll talk about some ways that we're using it to bring some scientific machine learning tools to bear on power system simulation problems. Okay, so let me first talk about this first question, our low inertia, large scale grid, small signal stable. So this is work that's actually done in collaboration with a team of people led by Gabriela Hug at ETH Zurich, led by Uroš Marković. So before I dive in, let me just use the definition of some acronyms as a way to kind of set the scene for what I'll be talking about. So what I'll specifically be trying to think about is, as I've suggested, this interaction between voltage source converters and synchronous machines. And so I'll use VSC as the acronym to define a voltage source converter. Think of a PV inverter or a battery storage inverter. And I'll use SM to denote the acronym for synchronous machines. And then things that will matter within these devices, and some acronyms that I'll be talking about are the synchronous reference frame, basically the reference frame that's being used for control within the voltage source converter, and then control loops sitting on the synchronous machine, the automatic voltage regulator, and the power system stabilizer. So the AVR is typically used to maintain a desired voltage magnitude on the machine, and then the power system stabilizer is something that's typically used to damp out undesirable dynamics happening at the system level. Okay, so let me talk just very briefly about some prior research. When we dig back into the literature to see how people have addressed this specific question about the interaction between synchronous machines and voltage source converters, I believe it's actually Reza Iravani and Phil Lane at Toronto back in 2007 who started thinking about these ideas in the microgrid context. So they developed models, detailed models that capture all of the electromagnetic phenomena and the fastest control, or at least the inner voltage and current control loops on the converters to understand stability in a microgrid context. Moving on a little bit later, it was actually Bob Lassiter and his postdocs and PhD students who a few years later started thinking about specifically what are the modes that appear to be destabilizing when we see, to the extent we see unstable events happening in these interactions between synchronous machines and power electronic converters. Again, a voltage source, or sorry, a microgrid focus in this work. And in that case, Bob Lassiter was not looking at some of the details about network design and the composition, like what fraction of voltage source converters you have in the system. So the work in my case, I would say, I think my co-authors have, everybody's got a slightly different opinion on what's motivated them to get to this point. But in my case, one of the papers that really inspired me to want to do this work was Yashin Lin's work, which actually just appeared in NAPS in 2007, where they were looking at small signal stability of systems with different grid following voltage source converter composition. But what I got very interested in this topic because of this paper, I think is a really interesting initial investigation of large scale systems, but they omitted things like network dynamics and some important control loops on synchronous machines and only studied, as I said, grid following converters. So in a way, the work that I'll talk about here is inspired by that initial effort to try to move the ball forward.
Duncan, just very quick question.
Yeah.
Why would one even think that they would be small signal stable?
Why would one even think? Well, so in practice, we see that at least microgrids can be small signal stable. One would hope that they're small signal stable because we're hoping to operate these systems.
Well, if you look at the structure, there is a paper that I will send you that was done 2-3 years ago that looks at the structure of the linearized model when you have just local controls responding to local outputs. And there is a structural system matrix that makes it, hint into that direction, but it could be parametric, could change. So I think it's probably worthwhile looking into why.
I'd love to see the paper. Yeah. Okay, great. I mean, what I'll show you is that, certainly, for detailed system models, there's a broad range of operating conditions in which we do observe just empirically from the model small signal stability, but then I'll show you what seem to be the dynamics that appear to matter the most when destabilization appears to occur. So then just to frame this gap and the core approach, what I'm hoping to show you today is what happens when we have a mixture of grid forming converters, grid following converters, and synchronous machines, which is what I would argue is the trajectory that power systems will be going toward or through in the future. And we want to also try to understand the role of network dynamics to the extent that we can model it in the ODE representation that I have, and I'll talk a little bit more about that, what might be interesting to think about in the future. Specifically what I want to do in this work is think about some of the importances of higher order synchronous machine models versus what folks have used in the past for these types of analyses. And as I've said, ask what physics or control loops are implicated in destabilizing when it occurs. So we take a differential algebraic equation modeling approach. So each single device we represent in a per unit representation, and then connect them with a network which has its own synchronous reference frame. The model validation, I won't show you results here, but we do model validation against a built-up Simulink model. There's other validation stuff that I'll talk about in the second part of the talk coming up. And then we simply do standard small signal analysis, including computing participation factors, and then look through parameter sweeps of how the destabilization appears to occur. So I should say that, conceptually, ultimately what we're doing is something quite simple, which is just a small signal stability analysis. And the real kind of effort in this research came about in just constructing the modeling frameworks in order for us to be able to address these questions. And that's going to come up a little bit later in this PSID tool that I'll talk to you about in terms of the time that it took us to get to this point. We're hoping that we can short circuit that time with this tool that I'll be talking about later. So I'll just talk very briefly about the type of models that we use. So for the synchronous generator, we have sixth order dynamics describing the machine physics. So that goes all the way down to subtransient reactance, plus 8 additional, mostly control states governing things like the automatic voltage regulator, the power system stabilizer, and then frequency control. All of this is represented in DQ for the synchronous machines. And these are details that, just so that you understand kind of some of the design choices that we made in the model. So standard kind of model formulation with a round rather than salient pole rotor, steam turbine as the prime mover, and then some sort of basic models for the turbine governor and the power system stabilizer and the voltage exciter. On the voltage source converter side, very importantly, and this is something actually that Dominic Gross was talking about earlier in a talk on Monday, we use a three-phase balanced assumption. And so we're not looking at imbalanced sort of fault conditions, and that's something that's really important for thinking about in future work. So the way that I want to just describe like the structure of this type of model is that you've got the device itself, so the power electronic device itself, which comprises, as you may know if you've thought about inverters before, a bunch of very fast operating switches that sort of chop up your voltage waveform that are governed by a pulse width modulated controller to give you the voltage waveform that you seek. So, and then we also have additional physics just describing an output filter and some impedance connected to the grid, where this grid then, I'll show you on the next slide, is an additional part that we model in the system. And then connected to that physics, we've got an inner control loop, and here's the synchronous reference frame acronym that has a voltage controller and a current controller. So think about sort of passing voltage and current set points into those control loops. And those are then, as I suggested before, on the order of sort of tens of milliseconds timescale, are seeking to ensure that those voltage and current set points are being met. And then we move over here to what we call the system level controller, the outer control loop, where you've got the device controlling both reactive and real power by either set point in the case of a grid following converter, or some sort of droop control mechanism in the case of a grid following converter. Okay, So very briefly then with the network model, the first simulation results that I'll show you here, we've got just a simple 2-bus model where we've got generators that have some local RL loads, balanced 3-phase flow, buses connected by a simple pi section model. And then, as I suggested, the first results are just with a 2-bus system, but I will show you, or I'll talk about what happens when we scale up to a much larger system where we have a 59-bus representation of the Southeast Australia system. Okay, so finally, now I'm at a point where I can start talking about what we see emerging as important dynamics. So with a simple 2-bus model, what I'm showing you here are results for, in this case, ignoring network dynamics. So that is that pi section model is just replaced with simple algebraic constraints connecting the devices together across the network. But I will say, at least in this case, when we look at network dynamics added on, that the sort of general characteristics of the conclusions remain the same. And that is that, so what we're looking at here on the x-axis is the penetration of first grid following converters. So we're starting, imagine we start with a system that's got just pure synchronous machine, and then we add to it in increments more and more grid following converters to pick up the load and then back off the output of the synchronous machine in response. And so that's what's happening on the x-axis here. And then let me actually I'll focus first on the bottom figure, which is showing you the real part of the largest eigenvalue in the system. And so then, of course, with a continuous time system, what we're concerned about is when that eigenvalue crosses over into the right half plane, at which point we've got instabilities arising. And so then in this case, we can see that it's at about 60% penetration of grid following converters. We see that that eigenvalue crosses over and becomes generates an unstable system. Here's what I think is interesting. So if you then ask, well, what are the participation factors associated with that unstable eigenvalue? This is basically just a way of saying, well, which state variables seem to matter the most, which get excited in that unstable mode. And it's a combination of the dynamics of the power system stabilizer, which is something that's basically addressing voltage on the synchronous machine, and then both inner control loops of the voltage source converter. So these two control loops themselves then are sort of playing off of one another to generate these unstable dynamics. So this is actually consistent with some things that that paper that I mentioned before, Lin et al. Saw, where they saw also that removing an automatic voltage regulator, which is ultimately controlled by the PSS, tends to stabilize the system. So you can imagine improving margins by changing the power system stabilizer gain or adjusting the inner control loop gains. But I just want to comment here that those control loops themselves are there to serve some very specific purposes. In the case of the PSS, it's to damp out undesired sort of slow mode oscillations, and then the inner control loops are there to ensure that the power electronic converter and all of its inner architectures work the way a power electronics engineer wants it to. So it may not be very easy to retune those, especially those inner control loops, which are generally kind of stacked in a very narrow bandwidth of time scale, considering all of the objectives that a power electronic converter has. Something interesting that I just want to comment on is that the inertia constant doesn't matter at all in these unstable events. So people have thought about low inertia systems as being these things to be concerned about because we're losing our rotating mass. But in this case, the reason that low inertia systems matter for stability is simply because of interactions on the control loops that don't have anything to do with that rotating mass. And then, as I suggested, the network dynamics, if we add those in with that pi section model, we see basically the same result. So then if we shift to thinking about synchronous machines versus grid forming converters, now we're looking at the same thing on the x-axis here, changing the penetration of the grid forming converters and looking at the real part of the largest eigenvalue. We can see essentially the same type of phenomena showing up again, although at higher penetrations in this simulation. so the instability in this case, it's ultimately from the same modes. That is, it's these inner voltage and current control loops playing against the dynamics of the power system stabilizer. And that's what happens here. And when I'm showing you, this is basically saying which state variables have the most important participation factors. So let's see, a couple of other comments. This one I think is pretty interesting. So this last bullet here is that when you look at this unstable mode, it's pure real. There's no imaginary component to it. So when we think about, sort of traditional ways of thinking about instability in power systems, is that engineers think about damping ratios. And are we getting to a point where the oscillations in various modes are getting undesirable? In this particular mode of failure, we've got just a pure real eigenvalue. And so thinking about damping ratios isn't really going to be a very productive way of thinking about whether or not we're approaching unstable dynamics. Okay, so now I want to talk about the network dynamics. And I want to stress that this is, I feel like we can and need to do much better here in terms of being able to describe network dynamics. So what we did in this study is we simply put in a pi section model where we've got some shunt capacitance and then resistance and inductance along the lines, rather than just algebraic constraints between our buses. So in that's, we call this like a sort of long pi section model that's meant to represent the kinds of dynamics that you might have on a long transmission line. So where the story seems to be changing in this sort of big scenario analysis empirical study is not so much on the dynamics of interactions between synchronous machines and voltage source converters. So the way I want you to look at this chart is, again, we're looking at penetration of a specific type of converter, and I'll tell you for each one of these curves what I mean by that, versus that largest eigenvalue. And so let me first just to sort of show you how the results I say don't change very much if we're asking questions about voltage source converters versus synchronous machines. The gold and the blue lines, the shaded out ones, are results from before, where it's that eigenvalue, its real part for a system without network dynamics. And the gold one is for the grid following converter penetration. The blue one is for grid forming converter penetration. And so then what you can see is that when we add in those network dynamics to the model of the system, that we still have a crossing over into the right half plane of that eigenvalue. In the case of the grid following converter, that is, it's almost in exactly the same place in terms of, grid forming converter, it's in the same place. Whereas with the grid following converter, we get slightly higher penetrations, but still an instigation of a small signal instability.
So Duncan, may I just ask or make a comment that every time we talk about these stability and in particular oscillations that go back and forth but don't blow up, you talk to the engineers like Lincoln Lab, they often said, well, but how do they say, the inertia of the rest of the system, in particular when you connect the synchronous machine to it's going to filter it out, because so it will average and it will never be seen in real time, real world microgrid. Do we need to model that, or what's your take at that? I can never answer that question.
Sorry, what's the specific question is?
Okay, the mathematics shows that you have these, pure imaginary oscillation at a certain frequency, right? But it is pretty high frequency oscillation. And you think about what's happening in the system. In the system, you have some oscillations being filtered out by different filters, by inertia of the machines for that matter. So by the time it gets to the load, does it really matter? I can never understand. People in power systems could never understand even low frequency oscillations, if they are dangerous or not, or they are just there.
Yeah,
I don't know the answer. That's why
I think part of the answer is that I don't view the inertia or those electromechanical, like Newtonian dynamics, to really matter in this case.
Filter, anything that has that slows down the process, filters out, will be fine.
Yeah. So Yeah, so in terms of whether or not those dynamics will be fine, what these results suggest is that the nature of those instabilities is important enough that we still see those instabilities sort of pushing through, in this case, maybe it's the inertia of the network itself, right, of the dynamics on the inductance.
This problem has a long history with low frequency oscillations, right? Between electromechanical, and they never know if it matters or not.
Right. Yeah, and I think that in practice, we've seen that it's so this is why we have power system stabilizers, and we see that those have been useful in preventing some kinds of undesirable slower timescale dynamics. But the question I think that we have now to address is, we have yet to get to these very high penetrations of grid following or grid forming converters. And I think we need to be able to understand what, are those dynamics ones that will actually emerge? And so here's where I think that I want to try to address, this thing that I was saying about the network modeling before. I think that, this is a very crude representation of the network. And that specific question about whether or not these dynamics will actually propagate over longer time or spatial scales, I think we need to start thinking about other ways of modeling the network, whether or not we go down all the way to something like a telegrapher's representation, or maybe we can just think about it as a sort of EMTP style representation of the network, sort of input-output port style approach. Maybe that's the way to do it, but I think this is a really important question. It's something that I'll sort of come back to at the end, which is just that we need a lot of progress on understanding which physics matters with yeah. And I don't know the answer yet. I think we're just trying to poke around in the dark here to see where we can get with conventional models, but I think that we need to really push the ball forward. So the last point really that I want to make with this slide is that it's this red line, which is comparing the dynamics, or looking at the dynamics that emerge in cases where we begin on the low percentage side. That's a system that's 90% grid forming converters, 10% grid following. So that would be over here. And then as we move our way up, we're adding how much grid following converters we have in the system. So when we don't factor in the line dynamics using this pi section model, we see that there is an unstable mode that emerges. But when we put those dynamics in, this kind of gets back to Maria's point, I think, that the converters, those fast timescale dynamics that emerge, are getting basically damped out by that representation of the physics of the network. And so then that unstable mode seems to actually be pretty well controlled. Okay, so just a quick discussion about what happens when we look at larger systems. The upshot is that we see essentially the same types of conclusions as we did with just that simple 2-bus model. So we looked at a much larger model of Southeast Australia, modified penetration of grid following and grid forming converters, and saw that the penetration limits are comparable, sort of in the 60 to 80% range of grid forming or grid following converters. You can get that far and remain stable, but then the simulations show small signal instability above those penetration levels. Okay, so recap on this one then. For the assumptions we've made, we see that there's not small signal stability in large scale low inertia grids when you have either high penetrations of grid following or grid forming converters. I think we're doing a really good job of capturing the dynamics of the devices themselves, but we need to push the ball forward, as I suggested before, in terms of understanding the dynamics of the network. Okay. I'm looking at how much time it took me to get through that, and I'm going to skip through question 2 and just talk about some of the work that we're doing in computation. So reflecting actually on what we saw with the answer to my question 1, fast timescale dynamics seem to matter. So that suggests that we need more computing capacity for very large scale systems. And I'll try to build up this case in a couple of slides here. And ideally, one would hope that this capacity includes state-of-the-art modeling tools and solvers so that we can leverage sort of, if we're having to do massive interconnection-wide type simulations to understand transient stability, then the question is, what kind of computational platform are we going to be using to do that? The thing that really inspired this work that I'm going to talk about here is what my collaborators and I view as a need for what I'll call a sandbox for researchers to understand things like inverter control dynamics. So if you look back actually at that work that I was just talking about, where we're looking at small signal stability, this just building the model was more than a year of a PhD student's life. I mean, it took just a tremendous amount of work to bring all of this stuff together. And so then if a researcher, at another university wants to think about similar ideas, but with a virtual oscillator control on the grid forming converter, or some new type of control on the grid forming converter, they want to update something else in the models, they're basically starting from scratch, unless that PhD student that dedicated a year of their life to building this model did it in a way that's extremely well documented and easily accessible to new researchers. So I would say that the lack of having this sort of sandbox for researchers to study things like inverter control dynamics or other modeling issues in low inertia power systems really hinders scientific reproducibility. And so we need to have some sort of a platform that we can all contribute to, and then come back and leverage state-of-the-art computing capacity. So let me just kind of set up then, coming back to the slide that I showed you before, what I was talking about in the first part of the talk was small signal instability events. Relatively easy to deal with from a computational perspective, because we're really just sort of putting together the ODEs and then just saying what are their eigenvalues. If we want to understand transient dynamics, that is what happens in a time series simulation to some sort of an event, now we have to start talking about numerical integration. And numerically integrating large scale systems across many, many time scales of dynamics gets really hard really fast. So let me actually just kind of set up that basic idea. So if you think about historically what we've done in synchronous machine dominated systems, for trying to understand these sort of transient time series simulations, we use explicit numerical methods, that is for the numerical integration, and maybe a number of ODEs that's on the order of a few hundred to describe the dynamics of these systems. As we move into inverter dominated systems, we're replacing, like for every one synchronous machine that you put on the system, you're replacing that with hundreds of inverter based resources, each with their own, potentially 15th or 16th order ODE model. But then the systems are also becoming increasingly stiff. And what I mean by that is that we've got more and more dynamics across many, many orders of magnitude of timescale that we have to be concerned about. And implicit numerical methods are the ones to really use in these sort of stiff simulation situations if you want to try to get through your simulation in any degree of reasonable time. So if we just think about what's happened historically within industry simulation practice, so there's two very large buckets of types of simulation approach. We have what we call positive sequence simulation tools like PSSE, Power World, or PSLF. These are modeling in the phasor domain, the dynamics of the devices that we're concerned about. And they're historically used to study electromechanical phenomena, that is those slower timescale dynamics. But they're, at least historically, unable to capture the very, very fast dynamics that we might be concerned about that I showed you emerging in unstable modes in the first part of the talk. Part of the reason for that is just in the modeling assumptions that they have to use in order to represent the network interface between a device and the network itself that they're trying to simulate. But they're useful for large-scale system simulations. If you're interested in capturing as much of the physics as you can possibly imagine, then you're going to turn to using what we call an electromagnetic transient program, something like PSCAD. So this can capture both electromagnetic and electromechanical phenomena, can do a good job of describing those fastest control loops, on the converters that we care about, they're suitable for simulating small power systems, but because of the size of the models that you have to build with EMT simulation packages, they're generally intractable or not practical at all for very large scale systems. So let me actually then just give you an example. So one of my collaborators, Brian Matthias Hodge, has actually been working with an EMT simulation version of the island of Maui's electric power system. And just to give you a sense of like the time that it takes to understand the dynamics, one 30-second EMT dynamic simulation of Maui takes something on the order of 5 hours to run. And so if we think about Maui versus something like the Western interconnection or the Eastern interconnection, if we're trying to understand how the fastest timescale physics matter in a simulation environment like this, it's clearly going to be impossible to do with an EMT solver for something like the Western interconnection. So this is where this tool that we've built, Power Simulations Dynamics, comes in. What we're trying to do, as I suggested, is build a sandbox for researchers to work with, but also sit in between the fast timescale simulations that you can get from something like, or sorry, the rapid simulations you can get with something like a positive sequence simulator, and the very, very slow but faster or higher physics, higher degree of accuracy physics representations of an EMT simulator. So we built the tool in Julia, which is an extremely powerful scientific computing scripting language. And we built it as an open source platform in order to study, as I said, system stability in low inertia power systems. And we're focusing on two parts. Actually, the part that we've been focusing on the most now is just building data modules and modularity that enable other researchers to pick up the tool and do fast model development if they wish. So for example, just take a model of a power electronic converter that somebody's already developed and just swap out the inner control loop or swap out that outer control loop with something else. The reason that Julia, I think, is a really exciting language for us to be working in is that it's just on its own, it's extremely fast from a computational perspective, but it also gives us access to new cutting edge solvers for large, stiff systems, and also enables us to use auto differentiation functions for fast Jacobian calculations and all of the other sort of derivatives that we need to be computing in these kinds of simulation environments. So our vision is to use this tool to enable scientific computing approaches to do things like studying questions about the physics of the system. How is model complexity versus fidelity traded off? Can we benchmark emerging converter control strategies? And then in a use case that I'll talk about in the last little bit of the talk, can we leverage scientific machine learning tools to accelerate computation? So it's been a lot of work for us to get to the point where I can show you a figure like this, where I'm showing you just a time series simulation of our tool PSID versus a use case of a 14 bus model built up in a positive sequence simulator called PSSE. But we're getting excellent comparison between, sort of existing industry standard tools in simulation and what we're capable of doing in PSID. So as I suggested, it's an open source architecture. And so part of the reason that I'm excited to give this talk is just as a bit of advertising to see it, to hope that others might get interested in getting engaged and involved. So we encourage you at a minimum just to work with the tool and use it to flag areas where the rest of the folks on the team can improve it. But we also are open to having others take part in the open source development. And we have a Slack channel. This is done in collaboration with a principal investigator named Clayton Barrows at NREL. And so the Slack channel is hosted as NREL-SIIP or SIP. So, okay, so now I've got just a few minutes to talk about how we're using the sandbox. So we're really excited about a recent project that we've kicked off with funding from the Advanced Grid Modeling program at the Department of Energy to look at approaches to use scientific machine learning to accelerate how we simulate these very large scale systems so that we can take that, for example, 5 hours to simulate 30 seconds of time series and make it a more tractable period of time. So at a very high level, there's two approaches that we're pursuing for this sort of acceleration. So the first is to learn new models of the physics to accelerate simulations. And we can do that by just trying to reproduce the time series directly without having to integrate an ordinary differential equation. That's what I call learning X. Or we're also building models where we're learning X dot, meaning we're trying to reduce the complexity of the ODE models that are then ultimately outputting an X dot that you can numerically integrate with a learned model that is faster to compute. The second big bucket of categories, and this is in particular being done in collaboration with the Julia lab at MIT and Chris Rackauckas and his students, is to get under the hood of the ODE solvers and to look at ways to improve the efficiency of those underlying implicit solvers. So the example of the motivation here is that implicit solvers, they do a lot of root finding, if you've learned about these things before, and that step can take quite a lot of time. And so we're looking at machine learning tools to accelerate that process, to basically learn how to find the roots faster. So I see that I am almost out of time. So maybe I'll just use this slide to say we're looking at this learning X as an initial use case where we're trying to build models that will directly output a time series simulation or a time series of system dynamics rather than having to numerically integrate the system. And so what we're leveraging is some work, actually, this is also work that was originally done in Chris Rackauckas' group at Julia Lab on echo state networks, or in particular, something called the continuous time echo state network. And perhaps so I can leave open some time for questions. I can talk about this more if people want to, but the basic idea is that we're using a neural network representation of the dynamics of the system to be able to do parametric studies. So we learn dynamics of the system for a few points of parameter choices like grid following penetration in a dynamic simulation. And then we can pick up that learned model and look at alternative percentages of grid following versus grid forming penetration that we didn't actually simulate in the numerical model, where those are just directly output by the machine learned model. Here's some just preliminary results looking at comparison between a directly numerically integrated model versus our, and that's out of sample, learned model. And you can see that there's just in these early examples some good comparison for different parameters governing how much converter interface generation we have on the system. So we're able to capture, at least in these very small cases, the dynamics with decent accuracy. We need to sort of source this around more with industry to see what's the accuracy that they might expect approach. Okay, closing thoughts. So we see some early results indicating low inertia small signal instabilities are realistically possible. And then I'll maybe just cut to the chase. I think there's tremendous need and potential for bringing scientific computing tools into the power systems community. And we hope that some of the stuff that I talked about in the second part of the talk will get some traction in that direction. So in terms of future, I really want to kind of stress this point about digging further into the physics of power systems to understand what we really need to model to understand those fast timescale dynamics. And here's something actually Dominic Gross was talking a bit about this earlier in the week. Is there a path to stability guarantees for these low inertia systems when we're representing all of the physics that we really think matter? And I will stop there. Thank you all for your time.
Thank you very much, Duncan. A lot of things to think about. We have just a quick few questions. I think you have 3 minutes. Tong Huang, maybe you want to ask your question. I think you're unmuted.
Yes. Can you hear me?
Yes.
Thank you for the presentation. I learned a lot from your presentation. I have one question about the faster switching dynamics of the inverter.
Yeah.
Typically, inverter have a very fast switching dynamics, and they may inject some harmonics to the grid. So I'm wondering, will this faster switching dynamics impact the grid operation?
This comes back to Maria's question earlier, I think, and the general, the sort of consensus of opinion seems to be that those fast switching dynamics harmonics don't travel very far spatially, and that's certainly true. There's a possibility that in very large scale penetrations, they travel enough, maybe a very diminished amplitude, that you could excite some undesirable mode. But my instinct is that that's unlikely, but I think it's something, this kind of gets back to what I was saying at the end, the charge. Yeah, is that I really think that we've got to get a framework for thinking about these physics in a more systematic way.
I see Bernie, he held his hand up. So Bernie, hi, you want to ask you a quick question, comment?
It's along these same lines. So when there's new devices on the network that introduces new ways we can make the system unstable, so that's perhaps not surprising, and then we need the new controllers to deal with it. But this idea that voltage controllers go unstable among themselves is not new. In fact, it's a common problem at a power plant where you have multiple generators. And so there's strategies that the voltage regulators don't fight it out and go unstable. I wonder if there's anything to learn from those type of controls.
I'm glad that you're asking that question, Bernie. Thank you.
Yeah, no, that's a really well taken point. And one of the things that I'm a relative newcomer to thinking about these dynamics, and I think it's fascinating stuff, but I know that there's decades and decades of history here for me to learn more from. And so
I think, Bernie, what's different, I think that it's what is the valid model to use to capture those, and its time scale. It's much faster. Yeah. So the models that we use even for transient stability, I made comment myself, they're not valid because you are not going to see, what's really happening, ERCOT reported that or whatever. So there is a new problem there at that time scale, but people use, you did mention, Duncan, RTDSs, but like MIT Lincoln Lab just does that. And I think your answer probably is what you are doing, I joke with my students, we are doing a poor woman or poor man's RTDS, with its computational things. Nobody can pay for that scaled up RTDS, right?
But I think, Bernie, I think your point is really well taken, though. I mean, so Maria, I totally agree that, we're talking about sort of new dynamics in physics, but it could be that the strategies to solve that problem are identical to what have been used in the past to deal with.
Well, this is not to say that we have solved those problems. Anyway, I think it's 12 o'clock. I think we have to let Duncan go because he has time conflict. It would be great to continue. If you guys have some more questions, I can send them to Duncan. We'll forward and answer later. Thank you, everybody.